Under standard conditions at 25 degrees Celsius, solid zinc reacts with cobalt 2 plus aqueous to produce solid cobalt. Write the balance equation for the oxidation half reaction. Then write the balanced net ionic equation for the overall reaction and calculate the standard potential energy for the overall reaction at 25 degrees Celsius. The balanced half oxidation reaction is zinc solid forms zinc 2 plus ions plus 2 electrons. Cobalt 2 plus ions lose 2 electrons to form solid cobalt. So solid zinc gains 2 electrons and becomes zinc 2 plus ions. So the balanced net ionic equation for the overall reaction is solid zinc plus cobalt 2 plus aqueous yields solid cobalt plus zinc 2 plus aqueous. To calculate the standard potential energy of the overall reaction, we add the standard energy of the oxidation reaction plus the standard energy of the reduction reaction. In this case, zinc is oxidized and cobalt is reduced. The oxidation half reaction is zinc solid forms zinc 2 plus ions plus 2 electrons, and the reduction half reaction is cobalt 2 plus ions plus 2 electrons yields solid cobalts. The standard oxidation potential for zinc 2 plus ions plus 2 electrons yield zinc is negative 0.76 volts, and the standard reduction potential for cobalt 2 plus 2 electrons yields cobalt is negative 0.28 volts. We have to flip the oxidation half reaction to put solid zinc on the reactant side. Also, since the reaction is spontaneous, the standard potential energy of the overall reaction must have a positive value. So to calculate the standard potential energy, we add 0.76 plus negative 0.28, or 0.76 minus 0.28, and finds the standard potential energy is 0.48 volts. At 25 degrees Celsius, 2 H2O2 aqueous decomposes into 2 H2O liquid plus O2 gas with a standard energy potential of 0.55 volts. The first part of the question asks to determine the value of the standard free energy change, delta G, for this reaction at 25 degrees Celsius. The equation to find delta G is delta G equals negative NFE, where N equals number of moles of electrons, F is Faraday's constant, and E is the standard potential energy of the reaction. For this reaction, N equals 2 because there are 2 moles of electrons necessary to balance the equation. So delta G equals the negative value of 2 times 9,648.5 coulombs times 0.48. So delta G equals negative 92,625 joules. Next, we want to determine the value of the equilibrium constant, K, for the reaction at 25 degrees Celsius. We can solve for K using the equation delta G equals negative RT times the natural log of K. R is a gas constant and T is a temperature in Kelvin. So negative 92,625 joules equals a negative value of 8.314 times 298 times the natural log of K. So K equals E to the negative 92,625 divided by negative 8.314 times 298th power, which equals 1.72 times 10 to the 16th. And there are no units for K. The standard reduction potential, the half reaction O2 gas plus 4 H plus aqueous plus 4 electrons yields 2 H2O liquid, has a value of 1.23 volts. Using this information, in addition to the information given above, determine the value of the standard reduction potential for the half reaction below. O2 gas plus 2H plus 2 electrons yields H2O2 aqueous. We already know the standard reduction potentials for each of the half reactions needed to add together to find O2 plus 2H plus 2 electrons yields H2O2. However, we need to flip the second half reaction and its E value so that the H2Os cancel out. So the standard reduction potential equals 1.23 volts minus 0.55 volts, which equals 0.68 volts. In an electrolytic cell, solid copper is produced by the electrolysis of copper sulfate aqueous. Calculate the maximum mass of solid copper that can be deposited by a direct current of 100 amperes passed through 5 liters of 2 molar copper sulfate aqueous for a period of 1 hour. First, I convert 1 hour into 3,600 seconds. Then I convert from seconds into coulombs. There is a current of 100 amps, and 1 amp can be written as 100 coulombs for every 1 second. Then I convert from coulombs into moles of electrons using Faraday's constant. There is 1 mole of electron for every 96,485 coulombs. Then I convert from moles of electrons into moles of solid copper using the coefficients from the balanced equation. There are 2 moles of electrons because copper 2 plus ions lose 2 electrons to form solid copper. So there is 1 mole of copper for every 2 moles of electrons. Then I multiply by the molar mass of copper, 63.55 grams, and find the mass of copper produced is 118.6 grams.